I am Emanuela Luongo, a master student at University Federico II Naples. I would like to show you the early results of my master thesis project that I began at the Capodimonte Observatory, and I continued over these 2 last months during my internship at ESO. The purpose of my thesis is to investigate about the origins of Oosterhoff dichotomy and taking into account the formation of Galactic Halo. So the study involved error layer inside globular clusters and field error layer. Error layer are variable stars. They inhabit the horizontal branch in Hertzsprung-Russell diagram. There are population 2 stars, and the ages exceeded 10 gigayears, so we can find them inside the galactic halo, bulge, and globular clusters. Stellar atmospheres is characterized by radial pulsation, so we can distinguish 2 different types of pulsator, error layer C and error layer B. The first one has a smaller period and a shorter amplitude. The error layer B has a longer period and varying amplitude. Moreover, we can distinguish also them for the different pulsation mode. So error layer C has a first overtone mode and error layer B fundamental mode. We can also see this difference inside the Bailey diagram. On the right side, we can see the fundamental pulsator. On the left side, the first overtone pulsator. The same differences we can see in instability strip, so we can distinguish 3 different regions. The fundamental region, also in this case on the right side, first overtone region on the left side, and our region in the center where we can find both of the pulsator. In 1939, Peter Oosterhoff was the first one to notice that the globular cluster inside the Milky Way could be split into 2 groups, Oosterhoff type 1, with an average period of error layer B shorter than Oosterhoff type 2. Moreover, we can distinguish them also because the Oosterhoff type 1 is more metal-rich than Oosterhoff type 2. In 1981, Sandage seek an explanation for the Oosterhoff dichotomy using the Van Alabama and Becker relation. So basically, he fixed a temperature, assuming that we have a similar mass for each layer, so we can lead from the dichotomy in period to a dichotomy in luminosity. Moreover, in 1997, from Bono et al., they proposed the hysteresis mechanism. So basically, we can distinguish the 2 different types of Oosterhoff from 2 different types of instability strip. For Oosterhoff type 1, we can find inside the whole region the fundamental pulsator, while for the Oosterhoff type 2, we can find the first overtone pulsator. We have to remember that our aim is to link the Oosterhoff dichotomy to the formation of galactic halo. So we know that from the lambda CDM model, the massive galaxies evolved by devouring the lower mass galaxies. So basically, our halo is composed of stars and globular clusters that was part of these lower mass galaxies. The simulation studies have shown us that the debris inside the halo that is part of the same progenitors preserve the same structure inside the integral motion space. We can show here in this slide, we can see the E energy and the projection on the Z axis of angular momentum. Okay. The first part of my project is about the error layer inside the globular clusters. My dataset is made up of 158 globular clusters. The first information that I take is the 6-dimensional parameter to calculate the integral of motion. This information I take from Vasiliev and Baugart. Moreover, we want to analyze 2 types of classification. The first one will be the in situ accredited classification from the most recent paper of Belucoro and Krastov. Moreover, we want to analyze the progenitor classification by Callaghan. And finally, I find the most recent list of Oosterhoff type from Stobie and Sidney Vandenberg. About the in situ accredited classification, they used the method to classify the stars and globular clusters inside the halo with the classification is based on the ratio between aluminum and iron. They use AstroNN algorithm to calculate the integral motion with the Milky Way potential 2014. In our case, I use the Galpai algorithm just because it's easier for me to have the first approach to this matter, and Macmillan 2017 potential. In the right side, we can see the plot of energy and angular momentum, the projection of angular momentum. I divided the shape of marker into circle for the Oosterhoff type 1 and diamond for Oosterhoff type 2. We can note that on the left side, these two types of Oosterhoff is on our histogram, and we cannot see a clear correlation between Oosterhoff type and this classification. Moreover, about the progenitor classification, we have 8 different progenitors from Culligan. The classification in this case is based on the chemodynamical classification. So basically, they start from the assumption that each globular clusters could be distributed inside the 4-dimensional space like a multivariate Gaussian. So they use the algorithm of Agama with the potential like as Macmillan 2017. So also in this case, we use, of course, Galpai with the same potential. On the right side, we can see the same plot than before, so energy and the projection of angular momentum. And we can distinguish also in this case the Oosterhoff type 1 with the circle and diamond Oosterhoff type 2. For each color, I want to distinguish the different progenitors. And first of all, I want to highlight these 3 progenitors, main disk, main bulge, and Sagittarius, where we can distinguish just one type of Oosterhoff, Oosterhoff type 1. But this is not so significant because, of course, in the main disk and Sagittarius, we have just one globular cluster. The main disk and main bulge are the progenitors that occupied the more density, the region more dense, with the more density in our plot, or in situ region that we already said. So we can say that in situ could be just Oosterhoff type 1, but this is not true because there is also low energy progenitors that balance this count of Oosterhoff type. Finally, I want to highlight that Gaia Enceladus and Hermes stream shared the central bulk, and this will be important for the next part of the project. Finally, I just want to highlight all the progenitors that we collected from the comparison with the Culligan. So, in conclusion, about the globular cluster, we cannot see a clear correlation between the Oosterhoff type and the ancient merging. We start from 158 globular clusters, but just 47 of these as the Oosterhoff type label. About the second part of my project, so field error Lyra, I collect almost 10,000 error Lyra AB. The information of 6-dimensional parameter come from Gaia Data Release 3 and from the Apogee, Gala, SDSS, and Lamos LRS. The progenitor classification, in situ accreted classification, and Oosterhoff type separation is done by hand in TopCat by me, just to have the first sight on my dataset. Okay, about the 6-dimensional parameters, so 3-dimensional for the position, 3 for the velocity. I want to highlight that radial velocity it comes from Gaia Data Release 3, Apogee, and Gala, but from SDSS, Lamos, and LRS, I take the information of redshift and I calculate the radial velocity with the following relation. Moreover, I calculate the distances, the photometric distances, using the 3 relations by Shili et al. And the classic distance module relation for the distances. The information of pulsation data and photometric data come from Gaia Data Release 3, while the linear coefficient come from the same paper than before. So basically, we can find the metallicity, the two magnitude. So our dataset now is complete because we have the distances, and we are able to calculate the integral of motion. But before, I want to separate my dataset into Oosterhoff type. So in this plot, we can see the Bailey diagram of my dataset, and we can separate this into Oosterhoff type. So I basically labeled the green circle, the star inside the green circle with the Oosterhoff type 2, because the period is longer than the Oosterhoff type 1. And I want to show just the density plot that it could be more clear, the separation between the two regions. So we calculate the integral of motion. We realize this plot of energy and the projection of angular momentum. We use also in this case GalPy and Macmillan 2017 potential. We decide to cut the dataset just to realize the same plot that we already seen for globular cluster, because we want to compare the situation of globular cluster and the layer in the field. Okay, from this plot come from Bellucorova and Krasov paper about the globular clusters, and we can note that there is the same shape separation, because we can note the central bulk and the most density region on the right side. The only one difference is that in this plot, we have the energy that is shifted because we use another type of potential than, of course, Bellucorova and Krasov. So in this case, I just want to highlight the two regions that we have separated. Also in this case, we cannot see a clear correlation between the Oosterhoff type and this type of classification. About the second classification coming from Callaghan, we have also in this case 8 progenitors, and we want to compare the plot that we already seen with the globular cluster and the field area. First of all, I want to highlight the main disk and main bulge. They share this most density situation. Low energy also, we can notice that is in the center near this most density region. All of these 3 progenitors, of course, occupied the same region in situ that we already seen. And finally, I want to highlight the Helmi stream and Gaian-Enceladus. They share also, in this case, the central bulk. Finally, we can note Sequoia on the left side, most density region, and Sagittarius on the right side. So in this plot, I just want to highlight all the progenitors, like we already see for the globular cluster in the first case. So basically, we cannot find a real correlation between the Oosterhoff dichotomy and these 2 types of classification. The work, my project is in a work in progress, of course. So what I want to do in the future, I want to compare my photometric distances with the parallax distances by Baller-Jones. And I want to find some other method to classify the progenitor and to separate, of course, Oosterhoff type, different progenitor, and in situ accreted classification. Thank you.